Yeah, we're not finished.
Good afternoon, everyone. So just a couple of points before we get started. So homework two, I'm not sure why quite a few of you had assumed the coefficients for cos and omega t would be zero. When I did do the example in class, I explicitly mentioned I took the very easy case of duty cycle 0.5, which is perfectly symmetric, f of x equal to 2 equal f of minus x, negative f of minus x. That would allow us to just make it be modeled just using signs alone. Right? For all of the duty cycles, the coefficients would have to involve cosines as well, in addition to sine. So some of you, I noticed at least 6 of you had left out or assumed the coefficient for cosines would be 0 in the Fourier series. So that was one mistake. And then a couple of you had drawn the waveforms for the third problem with switch Q1. So you all got the duty cycles for the most part, correct? You got D1 equal to 0.25, D2 equal to 0.75 for the case where VO was negative 25 volts. So you put Q1 as 25%, which was absolutely correct. And then in class, when I drew it, I drew Q3 to turn on at the same time as Q1, but then last longer and move on. Right, so this is what we have done in class. Some of you had phase shifted this Q3 a little bit further out. Which is okay, so some of the assignments that I saw, you had this time period synchronized, so Q3 was looking like this. Right, instead of the turn on time both starting at the same place. So that is going to be a bit of a problem. So in the first case, when you have Q1 minus Q3, you will see that in this section, it's going to be 0. In the second portion, it's going to be negative 100. In the third portion, it's going to be 0. And then the same pattern keeps repeating. Okay, so this is Q1 minus Q3. The way some of you drew, which is Q1 minus Q3 prime, you would have some portions where it's positive 100, and then the rest of the portion where it's negative 100. So positive 100, negative 100. In this case, we are just going from 0 to negative 100. This is absolutely fine too, because we do the average, you would still end up with the same negative 25 volts. Right? But the only problem is here you're switching from voltage level of 100 to negative 100, while here you're limiting your switching from 0 to a negative 100. Right? So you would prefer, most of the time you would prefer to have a lower switching voltage level because that would reduce your THT, and your dV by dt as it reduces, you would end up putting less stress on your components as well. So there are advantages to keeping it in this form rather than this form. That's why we start off Q3 synchronized with Q1. Right, so you make sure that the turn on happens at the same time. The turn off can be out of whack. All right, so that's the reason we went with this method. But again, either way you put it, you can phase shift it however you want. You will still get that same average value. It's just that you want to reduce the rate of the change from the higher level to the lower level as much as possible. Right? But otherwise, most of you got the assignment fine, so not too many mistakes. And whenever you write any MATLAB code or anything, just attach the code as well. If you can't attach an M file, just convert it to a PDF and attach it with the homework. Anybody have any questions about the homework? For last week, homework for this week? Right. So last class, let's quickly do a review of what we covered last class and then jump on the things that we need to do this class. So last class we simplified and cleaned out our Maxwell's equation with a lot of assumptions that would be applicable for our machines course that we are going to be looking at going forward. So the first equation that we have is if you go around the loop and integrate the magnetic field, that is going to be equal to mu naught times the current enclosed. Again, remember that this is current enclosed. This is not just the current of a conductor, as we will see the distinction in today's class. Right? That's the reason I'm carrying on this enclosed subscript from lecture 3, right? Lecture 5. So the second thing we defined in our previous class was the term flux. So if you go around the surface and if you integrate the magnetic field emanating out of the surface, that is going to be defined as the flux. And if you do it for a closed surface, for instance, a sphere or a cylinder, any kind of shape, but it needs to be completely closed, then the flux is going to be zero. Right? This is what magnetic, there is no magnetic monopoles mean, where all the field lines leaving must terminate back, whatever flux leaves must come back in. And we looked at certain analogies for this. Campfire case, or you have water coming out of a pump in a closed system, whatever water goes out must be the water coming back in. So all of those are similar scenarios, but theoretically they are not the same because the way this magnetic field works is where it's conservation of energy or conservation of mass. So the last one that we simplified was the Maxwell second equation, which is basically the Faraday's law, which is the EMF that's generated across a coil is going to be proportional to the rate at which the flux is changing through the coil, right? And we did make sense of what the deriving means, which is what the Lenz's law states, right? If it says that whatever, if you were to close the circuit where the EMF is generated, it would then create a current that would try and oppose the changing flux outside. That's what the negative sign means. If that is not there, then the current would be in such a way that it will keep creating more flux, which will create more EMF, which will create more changing flux, more EMF. It will become an infinite loop, which the power balance won't, energy balance won't make sense, right? And then the last equation, which we are yet to simplify, is the Lorentz force equation, Q times V cross B. So today's lecture, we'll get rid of this as well and replace it with another form, which I've already seen, L times I cross B. So that's what we'll try to do in today's class. All right. So going forward, you can forget all about Maxwell's equation. Just these three equations are what are required for it. And then the final equation that we're going to be simplifying today. So last class, again, we looked at this example where we have this kind of like a U-log bar with a rod moving on it. And we looked at two different scenarios where the magnetic field is maintained a constant, where the bar is moving. And then the second case where the bar is fixed a constant, that is velocity is zero and the magnetic field is changing. For both of those cases, we derived the EMF. The first case, we derived it using the Lorentz force equation where the charge, the bar is moving, thereby the charges within the bar is moving, so it's experiencing a force. Right? That force is going to move the charges around with positive coming down, the negative being going up, and that would in turn create a EMF, which we can measure. And if you connect an electrically conductive path, then the current starts flowing through it. Right? Otherwise, the material can be anything. It can be a conductor, it can be a wood, whatever, or the material will be there in the first place too. In either case, we will have an EMF that's developed across the bar. Right? And this again is the fundamental equation that we derived using the Lorentz force equation, but it also links back to the Faraday's equation that we have learned from high school. And then the second case is a little bit tricky, where the rod is fixed, but the B field is varying. In this case, the Lorentz force equation doesn't apply anymore. Okay? So we have to go back to Maxwell's second equation, which says the curl of the electric field is equal to proportional to the time rate of change of the magnetic field. And then we plugged it into Stokes' equation, we did some simplification, and showed that the Stokes, the Maxwell second equation, once you put it in Stokes' theorem, is exactly same as a Faraday's equation that we have, V equal to negative d phi by dt. Right? So those were the two cases we looked at, and then we went on to derive the power equation. I'm not going to go over the details again. The video is recorded, so you can take a look back at it. So basically, we have our expression power equal to EMF times the current. And we're going to be using this equation again and again. It's not a definition. We derived it in last lecture. And then finally, we looked at the derivation for a solenoid, what a magnetic field inside a solenoid looks like. So we have put some constraints on what kind of apparatus that we can analyze with the knowledge that we have so far. The first constraint is that these conductors are packed very tight together. And the second constraint is the width of this, the diameter of this core on which we wind it. It could even be an air core, basically a coil. The diameter of the coil must be very small. The first assumption, let us make the first assumption that the conductors are packed tightly together allowed us to simplify the fact that in between the conductors, if I have two conductors, let me draw them a little bit far apart just to show what's going on. The magnetic field due to this conductor is going to be anti-clockwise. The magnetic field due to this conductor is also going to be anti-clockwise, two consecutive conductors. So if you look at the magnetic field in between, the vertical components cancel out. Right? So if the conductors are packed close together, the vertical components, anywhere you can take it at any particular point. So here you have some field like this. You have a horizontal component, vertical component. Same thing which is going to happen here. You have a field like this. There is a horizontal component, there is a vertical component. This vertical and this vertical will cancel out as long as the conductor are jam packed together. Right? That was the reason we assumed that the conductors are very close together. And the second assumption that the conductors are not far apart vertically would allow us to eliminate the magnetic field outside as well. So magnetic field due to the first conductor compared to the magnetic field due to the second conductor. First conductor is going to be anti-clockwise, second conductor is going to be clockwise. So outside they are going to cancel, inside they are going to be adding up. Right? So that's what we saw last class. And once we have figured out, we make the assumption that outside magnetic field is zero because the diameter of the core is very tiny compared to the length. We can then go ahead and apply our the integral B dot dl over a closed loop equal to mu naught times I enclosed Ampere's law to figure out what the B field inside is going to be. And that's what we figured out as mu naught Ni divided by L. So this was where we stopped last class. Right? And of course, there is a problem with our assumption that B field is outside is equal to zero, which means we have created a magnetic monopole. So if I say there's only B field inside, that creates a problem where there is, if I could draw a closed surface over which magnetic field is always leaving but nothing coming back and no flux is coming back in. So that will violate our no monopole law. So what in essence is happening is this B field is actually completing the pathway through the outside world, but the area outside is extremely large. So these B fields spread from all the way from the top of the solenoid and bottom of the solenoid to all over space, going to infinity. So since it has a wide area over which it can spread out, that means the flux, whatever is coming from the outside, must be the same as the flux that's going through the solenoid inside. But that also means the flux outside equal to flux inside means that B out times A out must be equal to B in times A in. But A inside is constrained, right? So the cross-sectional area of the solenoid, that is going to be constrained by what the core diameter we used is. But outside there is no such constraint. So since the outside area is extremely large, B outside can be very small. So that's why we made the assumption that B outside is very small. If it's very close to zero, we can ignore it and just calculate B inside alone, right? But we are not violating any law. If you look at the flux out coming from the outside must be the same as the flux inside, right? Do you have any questions? Yep.
Yeah, if it was like a shielded device, would that affect A out, or is A out still like infinite in that case?
So when you say shielding, what would you do for shielding?
Like,
magnetic shielding is a very difficult problem.
Yeah, like maybe just like a shielded inductor. I'm not completely sure. I'm just wondering if that would affect the performance of the solenoid.
No, it won't. So you would typically, the way you would improve this B field is not by changing what's on the outside, but you would put some kind of material inside like iron or something which makes the B field stronger, right? So once you have iron inside, the B field has higher, so in this case, there is not only going to be B field inside, but there's going to be leakage B fields on the outside as well. But once you put iron inside, that has much better pathway for magnetic field lines to pass through compared to the outside air. So most of the field lines would now concentrate on the iron core. Right? Similar to when you have two resistors in parallel, the current would always go through the current would prefer to go through the path of the least resistance. Right? When we have an iron core inside, it creates least reluctance, the term I will introduce here. So the magnetic field lines will try to go through that pathway. Right? But in this particular structure, so the way I've drawn this open kind of structure, but in reality, the way you would do this is you would have something like a closed toroid over which you would wind these windings so that this pathway actually closes through the iron core and not through air gap like this. Okay? So this is how you would end up reducing the leakage component that we have. Any other questions? All right. So today's class, bunch of topics covered. Yeah, you can get through all of them. So let's start off with the first thing where we try and figure out. Oh, by the way, don't forget to mark yourself if you have participated in class and drop it off. But then let's see how I forgot to put it there. And those of you who have forgotten the previous class or something, just keep a track of it online. I keep posting it after every class, the scores. If I miss anybody, just let me know and I can award the points. Okay. So we have a silk solenoid coil there. And then switch out the direction of the current. So we pass some current through the solenoid coil and there's going to be some magnetic field B. right? If this current is a constant, then the B field from our expression, so our B inside mu naught n times I divided by the length of the solenoid, where n is the number of turns. Okay, so if the current is a constant, what is going to be the EMF developed across this solenoid? Zero. So if the current is constant, E which is equal to minus d phi by dt, again, these are only three formulas that we need. The last one we'll replace, but for now the only first three are sufficient to cover everything that we're going to be doing. So minus d phi by dt, and I define flux itself as integral B dot ds. So minus d by dt, integral B dot ds. If I is not changing, constant, then B becomes constant. Area of the solenoid is definitely not changing, right? The cross section, once you wind it, that's not going to vary. So if the area is not varying, the B is not varying, then the time varying component in this term is nothing. So this term just goes to zero, right? So when you have an inductor and the current is not changing in the inductor, the EMF developed across the inductor is going to be an absolute zero. So let's see what would happen if the EMF, the current starts to vary in whatever shape, doesn't matter for us. And that in turn means some EMF is going to develop. Right? And the way the EMF develops is its own magnetic field that creates the EMF as well. So we have this coil, and then because of this current, there is going to be B. So B due to I. And because of this I, because of this, so this is varying, not a constant. It's going to create a B field that is varying as well. A simple case can be, you can assume this varying sinusoidally. And then that is in turn going to create a B field in an ideal case to vary sinusoidally as well. And this varying sinusoidal B is now going to create an EMF across, let's consider this one tiny loop alone. Okay. We have a circular loop, right, over which the B field is varying. That means what, there's going to be an EMF that's developed across this loop. Okay. So the EMF that's developed across that loop is going to be minus d phi by dt. In our case, let's say this cross-sectional area is A. So there is going to be minus A times d by dt, right? And we have n of these loops connected in series. So this is a single loop. So just a single strand of wire that I create one loop, and you continue the same strand of wire to create multiple different loops. So all of these are connected up in series. So this starts here, goes around, completes a loop, then goes and keeps on creating a number of loops. So the total EMF, let me use capital E for it. Don't confuse it with the electric field. So that is going to be equal to n times d phi, negative n times d phi by dt, right? Or basically n times small e. Right? So let's go back and modify that equation just a little bit that we have there, because that was an equation for a single loop. So for when we have n number of loops, that equation becomes negative n d phi by dt. So that's the way you would have seen the expression in your high school textbooks. So when I have the solenoid, which is basically an inductor, what is going to be the energy in the solenoid? Anybody?
1/2 Li squared.
Half L squared. What do we get there? So energy again, we define in our third lecture as integral P dt. Right, and power again we derived last class, tau E times I times dt, and E itself was equal to E was A times dV by dt, and B, which I just erased from here, would be mu naught n times I divided by L. Oh, actually, sorry. Literally, will be equal to n times A times dV by dt. Again, every now and then I'll keep dropping off the negative sign. Don't worry about it, it's irrelevant. All you have to remember is just map if the current is increasing, then this is going to be positive, this is going to be negative. If the current is reducing or the flux is reducing, this is going to become negative, this is going to be positive. That's what we saw the sign convention in the last class. Right? So that the current that's going to be created if we were to close the loop outside would be towards the magnetic field, the flux that's increasing or decreasing, changing. So we have E equal to NAdB by dt, so the total EMF, and that in turn is going to be substituted for the value for B from here. We end up with mu naught n square. Mu naught n square A divided by L times di by dt. Now substitute this. So the total EMF across the inductor coil, the solenoid. Substitute this value back here. Again, this is the EMF. So our energy is going to be equal to mu naught n square A divided by L times integral I times this di by dt term times dt. So what we are left with is integral I di, which is just going to be I square by 2. So we have 1 by 2 mu naught n square A divided by L times I square. This term we are going to define as our inductance. Inductance L, right? So this term, this L is a function of the material structure, right? So how we wind this coil will change what this inductance value comes out to be. So this is not a constant definition in the terms of like how we define flux. It doesn't matter how you wind your windings, flux is always surface integral of the magnetic field. That is not the case with inductance. Inductance will change, similar to inertia, right? Inertia changes depending on the structure that you're looking at. So for the solenoid structure that we have, it comes out that inductance equal to mu naught n square A by L. For other structures, you would do the same principle. You would figure out what the energy stored in that magnetic field is, right? And then use the expression that same way how we substituted. So we have the integral of the power over time, substitute the back-EMF times current, and whatever term comes out outside, half I square removed out, whatever term remains, that you'll define as the inductance for the particular structure that we have. So when we go to motors, we look at different kind of structures as the motor rotates, what the inductance happens, how it changes, and all those. So this is not a definition for, it's not a universal definition, it changes with whatever the structure of the code that you have and how you want this winding. Any questions about? Yeah, thanks.
Is there an A missing in your total EMF on the left side?
Here?
No. So that definition of EMF is different than that, yeah.
Oh, no, this is, I replaced the 5 with B times area.
Oh, okay, my bad.
So, yeah, actually. So when I went from here to here, I replaced I as magnetic field times the cross-sectional area. Since the cross-sectional area isn't changing, once you wind the solenoid structure hopefully shouldn't change. So then flux, which is surface integral of B dot ds, just becomes B times cross-sectional area. Any other questions? Yep.
In that first example where you had little e equal to negative d flux of dt, could you just explain how you get to like a dv over dt?
Okay, so when you have flux, so flux is from our definition, right? Equation 2, surface integral B dot ds. So in our case, so that is basically, so to look at this one single loop that I have here, it has a cross-sectional area A and some B field perpendicular to the cross-sectional area. Right? So the surface integral B dot ds is just going to be equal to whatever the B field perpendicular to the cross-sectional area times the area A. Right? How did we define surface integral? When you have some kind of surface here and we had some B field here, we split it into tiny sections of area where the B field is not varying. Right, so let's say this here is B1, the field here is B2, so on and so forth, and this area is DS1, DS2, so on and so forth. So the surface integral was B1 DS1 plus B2 DS2, so on and so forth for all the continuous things. Right? If this B is the same across all the surfaces, then you can pull the B outside. So it's the sum of all the tiny surface areas, which is equal to the total surface area. Right? In our case, the magnetic field inside is the same, right? Across it, because how you do the draw the loop. So when I had this set of conductors in this 2D diagram that I can draw a loop like this, or I can draw a loop like this. As long as the loop encompasses the internal part of the solenoid, the B integral B dot dl is going to be equal to mu naught times Ni. Right? So B here is going to be the same as B here is going to be the same. It's going to be the B underneath it and everywhere. So inside the solenoid, the B is constant across the full surface area. So in this integral, I can pull the B outside. So it's just surface integral of a surface, which is just equal to the cross-sectional area of the surface.
Why is it then dB dt instead of just B?
Here,
Yeah.
oh, this B is not varying across the cross-sectional area, but with time the B is varying though. Right? So here, when I start passing sinusoidal currents, the magnetic field is also varying sinusoidally with time. So the area is not changing. Irrespective of what I do with the currents, the area is going to remain the same once I wind it. Right? So let me add one more step here before I jump. So this would have been d by dt. So I can replace flux with d times area. Right? This area I can pull it out because it's not varying with time. But the b is varying with time because I'm changing the current. So it would end up becoming negative a d by dt. Right? Anybody else any other questions? So the energy in an inductor will half Li square. So the first lecture I gave you a formula for energy density of a magnetic field. You have mu naught b square. We made a promise that I will do the derivation for that too. We don't assume any formulas. So once we have this piece of the puzzle, let's go back and substitute our values for inductance. So energy is equal to inductance is mu naught n square A divided by L. And then our magnetic field, our magnetic field B was mu naught n I divided by L. So I can rewrite current in terms of the magnetic field, BL divided by mu naught n, coming from this expression that I have here. So if I substitute this current back into the I square expression, you get B square, L square divided by mu naught square, n square, L square, L gets cancelled, mu naught square, mu naught gets cancelled, n square, n square gets cancelled. So I have half mu naught B square times the area times the length of the solenoid. Or the term B, cross-sectional area of the solenoid times the length of the solenoid. It's a pure cylindrical structure. This is going to be the volume of the solenoid, right? So you have the cross-sectional area times the length. And if you consider a cylindrical structure, that's the volume of the solenoid. So energy, the units of this is in joules, divided by AL, which is the volume, the units of which is meter cube. Energy per meter cube is the definition for density, energy density. 1 by 2 mu naught B square. So this was the equation we used when we compared the energy density of magnetic field compared to that of an electric field, right? There was the one final equation that we hadn't derived, but we assumed. So with that, we are done. So this derivation, I did it for this very specific case of an inductor. You can create, this equation is not specific for the solenoid structure. You can do the generic derivation for any magnetic field, but for that, that will require us to introduce a concept called vector potential, which gets a little bit tricky, and we don't want to spend too much time on electromagnetic theory. But I have posted the derivation, a generic derivation for any magnetic field B. The expression still comes out to be half B square by 2 mu naught. Sorry, 1 by 2 B square by mu naught. Okay? So even though we derived it for the specific case, it holds true for all cases. Anybody any questions? Okay, so let's cover this. So let's look at the final equation, force experienced by a conductor. So we have some conductor, we have some charges, and the charge density that time we saw is eta L, which is coulomb per meter. Density. So basically, if I want to figure out how much charge is there in 1 meter of this conductor, then it's just eta L times whatever the distance is. If it's 1, it's just multiplied by 1 meter. Okay, so if there is a single charge, and let's say there is a magnetic field, so this is a current carrying conductor, right, along the direction of the board, and then there is magnetic field coming from behind the board perpendicularly outwards. So this current carrying conductor is in a magnetic field that is coming from the backside of the board, right? And we all know it's going to experience a force. Let's say this charge can move along in this direction, right? It's going to experience a force pulling it downwards, and that force is going to be equal to Q times B cross B. Since the direction in which the charges are moving is perfectly perpendicular to the direction in which the magnetic field is coming out from the board, the product is just going to be, the cross product is just the product of the magnitudes, right? So this is for a single charge on one charge. Now, if I want to figure out the F on the total length of this conductor, let's say the total length is L, right? If I want to figure out the F on total conductor, then all I got to do is figure out what the total charge is there in the conductor. So this is the charge per unit length of the conductor. So the charge in the total length of the conductor is just going to be Q times eta L times the total length of the conductor times V times B. And this in turn Q eta L. Let me just move around these terms. V times L times B. What was this term? Q eta L B. Is the from the board? I think it was right here or right here. When we derive the power equation, we replaced one of the terms with Q eta L times V. Basically, the rate at which charges are flowing. Right? That's what this term is. So just L times the current I cross B. So what this means is going forward, we can forget about Lorentz force equation as well, because we won't be talking about charges at all. So going forward, if a current carrying conductor has some current I and it's in a magnetic field B in some particular direction or any direction for that matter, then the force experienced by the conductor, right? So we have B coming out of the board and then current going this way. So if I curl my hand from B to I, the force will be upwards, but I should go from I to B, so it's going to be downwards. More is correct. So we have L times L cross B, right? The current carrying conductor in a magnetic field, the force experienced is going to be in this direction. So another easy way of remembering this is Bill, but be careful. Force direction must be flipped. It's easier to remember, but the product is I cross B, not B cross I. Okay, so let's replace the last equation with that. We can forget everything we learned in last week. So we just have L times I cross B. Anybody any questions?
The U density, what is that? I'm sorry, I missed it.
Oh, this is the energy density of a magnetic field.
Oh, thank you.
So per unit volume, how much energy a magnetic field can take? Anybody else any other questions? So So right now we have figured out how a solenoid works. So we have some current carrying conductor, and this is going to create some magnetic field. And Ampere did the same experiment where he created a solenoid, passed some current through it, and he observed some magnetic field. And for whatever reason, he wanted to see what would happen if he put iron inside the solenoid, an iron bar inside the solenoid, right? So far we have considered an air core solenoid, but now we are going to look at it with a material inside an iron core solenoid. What Ampere found, so in both cases the current is the same, but he noticed that the magnetic field in the second case is orders of magnitude greater than what it was in the first case. Right? The current was exactly the same, nothing changed, just putting an iron rod, a passive iron rod, created a magnetic field that was much, much stronger. And he could not figure out what the answer for it was. So he came up with the reason that there are currents flowing on the surface of the iron. Right? So he said there are surface currents on materials. Some kind of surface current that's flowing on this material. So which then allowed them to still continue employing Ampere's law. So the solenoid itself has some current coming from the external source. Right? So this is some current I and going out. So this is going to be called I conductor going forward. And if we put an iron core inside, that in turn has its own surface current. That is what Ampere at least thought. Some surface current which purely flows on the surface of the material. So now if you draw a loop around this and do integral B dot dl, it's going to be equal to mu naught times I enclosed. Right? And then I enclosed has two components now. One is the conductor current, which we inject externally, intentionally, and another current, which is the material current. Okay? So it's component of both this current that's externally outside and the current that's flowing in the material surface. This model is of course absolutely wrong. Ampere did spend a significant portion of his time trying to measure the surface currents for different material, and he never could because that's not how things work. So what essentially happens that's the reason we have been using the term enclosed so far, because there can be multiple sources of the current in different models that we have. Anybody want to take a guess? When did we first discover ferromagnetic materials or their property where they amplify magnetic field or feel a strong attraction towards magnetic field? It must predate Ampere, right? Any guess? Yep.
The Greeks?
The Greeks, that's a very good guess. You want to get the time period? Different civilization got it at different time period. Ferromagnetic material, what's the first material that comes to mind when I say ferromagnetism? Iron. When was the Iron Age? Greek Iron Age, around 1200 BC to 700 BC. Different civilizations hit Iron Age at different time periods, but the Greek, the Western civilization typically is around the 1200 to 700 BC. There was a very critical event that happened just before 1200 BC. There's a very okay movie about it too. We might not even born when that movie was released. Troy. Right? So the Trojan Wars was just before this time period. So if those of you who have seen that movie would see glaring discrepancies. They end up using tools which are made out of iron, even though iron didn't come into picture much after the Trojan Wars had happened. And we don't know exactly when iron ore was mined and extracted, and the magnetic field property of it was actually discovered, because this period is also the Greek Dark Ages. Before this period is when we have those great Greek textbooks, right? Iliad and Odyssey and stuff. So after the time period, for whatever reason, some Greek civilization seemed to have collapsed or became a little bit nomadic. And all the text during the time period either was not written or doesn't seem to have existed at all. So we don't know exactly what caused it or what happened during the time period, but excavation does show that iron equipments have been found during the time period. So the earliest instance that we know of people writing about ferromagnetic material is this guy called Tales of Mind Eaters. Greek. Anybody remember the my Thales theorem? 6th standard, 7th grade geometry. Take a circle. If one of the side of the triangle is the diameter, then the angle of this triangle would always be 90 degrees. Right? So that's the Thales theorem. So he comes up with this theory to try and explain ferromagnetism. One such theory. So Ampère himself had this idea that currents flowing on the surface is what is creating this property of ferromagnetic material, a bit advanced. But during Thales' time period, so this was around 600 BC. So he comes up with this idea that materials have souls. So iron has some intention to create these field and then move this particle about it so that it can try and attract them, pull them. It's somewhat looked upon as if it's a joke now, but it's a very serious thought, because before this, people didn't believe in the idea of self-determination. It was always of the idea that everything was predetermined, everything was decided by some almighty or whatever. Right? And here comes a guy and gives a theory that things can be decided by whatever we have. In this case, he attributed to iron, which is not how it works, but it's a significant deviation from what the initial thought cycle or the philosophy of the time period was. So after this, here comes Epicurus, around 300 BC. And he comes up with the theory that this is where the initial idea of field lines comes into picture. Right? Much before Faraday, when he introduced them in around 1820, after those iron firing experiment to figure out what the fields look like. Right? So Epicurus has this idea that basically iron create these atoms which it pushes out, and these atoms flow around and then comes back into the iron. So any ferromagnetic material pushes these atoms out, and what then he said is if there is another material like an iron material or something, a ball or something nearby it, once these atoms move out of the way, it creates a vacuum that pulls in the ball that's externally outside. So this again is an initial idea of what the field lines look like and so on and so forth. This again would not explain why glass or something is not attracted, right? Why ferromagnetism is only particular to iron or cobalt or nickel and those kind of materials. So anybody know what Epicurus is famous for, the Epicurean dilemma? Did anyone take a philosophy class in your first year? Okay. So he puts forth this three statements where if he says that if so during this time period is the same time period that Socrates and his student Plato later picks up and changes the philosophical idea of the time period. So we have the early religions, if you see, they don't have this concept of nobility or more morality for God or whatever. This is all the later time period, especially in Christian religion after the Socrates time period, where some kind of good or evil is associated with divinity. The Hellenistic God don't have those principles, right? They do something, it's not for the good of people, or they just don't care. That was the principle. So Socrates was of the idea that there is some good going on in the world, and God determines what's good, what's wrong, and people doing good will go to afterlife and all those kind of ideas. But Epicurus didn't buy into any of that. So he had this simple concept where when Socrates said, God is omnipotent, omniscient, and benevolent, he poses a simple question. If God is all powerful and God can see everything, so he sees all this evil and he has the power to change all this evil. If he's not changing it, then he's not benevolent. So if God is benevolent and he is all powerful, so he has a need to change it and he has the power to change it, but he doesn't change it, that means he is not seeing everything, right? And if he can see everything and he's benevolent, it is just that he does not have the power to change it. So the Socrates statement that omnipotent, omniscience, and benevolent would not hold, because if it's all three, then there should be no evil in this world, right? So that's the Epicurean dilemma. But again, his influence in our philosophy is significant, but not in the later part of religion, because most of those were influenced by the principles of Socrates and Plato and so on and so forth. So this is a very good theory introducing us to field lines. And then of course comes our Ampère, a huge jump in between time period. People still couldn't figure out what was going on the iron that makes it so ferromagnetic. So he comes up with this idea of surface current, and then Ampère tries to measure it, fails. And then, of course, comes the atomic model in the early part of 19th century. Right? Then comes the idea that, hey, probably there are some neutrons and protons in the center, and then there is electron that's revolving around this. And if you look at this model, these electrons revolving is similar to like a current carrying conductor forming a loop. Right? So if you have a current carrying conductor that is going in a loop like this, then it's going to create a magnetic field that's perpendicularly outwards. Right? So there came the idea that probably magnetic field is because of these tiny electrons rotating around these central nuclei, which is then creating their own tiny dipole. And when there is a current carrying conductor creating its own magnetic field, these all align along that external field, amplifying the magnetic field that's being created by the current carrying conductor. There's a very big flaw in this model. Everybody who took electromagnetic theory course, what's the problem with this model? Yep.
That fact that there's monopoles,
There's what?
that there's.
Oh no, this won't create a monopole. Similar to if you have a current carrying conductor and a magnet, I just blew the one on the top, but I would close the loop back. Okay, so these field lines do always close. So here too, the field lines would close. So on the top surface, we would have the field coming out, on the bottom surface, it would come back. Let's take the idea.
Electrons don't actually follow an orbit like that.
Right, what would be the problem if they go on an orbit like that?
I'm not sure, but I know the electron cloud is a.
Perfect. So the reason this model failed is because when we have Earth going around the sun, we don't radiate energy, right? But when we have a charge that's going around another charge on an electric field, it is basically accelerating because it's going in a circular motion, right? So there's an acceleration happening. So whenever a charge is accelerating in an electric field, it is going to create radiation. So this charge will radiate away its energy pretty quickly in a matter of like 10 power minus 6 or 10 power minus 7 seconds. So by this model, there should be no atoms at all with any electron present, because they would radiate all the energy and the orbital would collapse and then it would go and merge with the nuclei. Right? So we will see stable atoms. Right? So this model is definitely not the way things work. So then come people who try and give a different explanation. Here comes the theory that it's probably the electrons spinning. So we have some electrons, it could be some electron cloud or whatever, right? And these are spinning around some axis. And this in turn, if you have a charge that's spinning around an axis, can create a dipole, a magnetic dipole, right? That can explain it, similar to a charge going around a circle, right? But in this case, the circle is basically fixed around the center of the charge axis itself. So this theory was quite popular for a few years, almost half a decade. But then this too again failed because they did measurements. And for this to be true, the electron has to be quite enormously large, even much larger than the nucleus for the amount of magnetic field we're actually measuring in ferromagnetic material. So that fails because we now know, or we have come to accept, that our current understanding is the electrons are point charges, literally point charge, right? So there is no central axis over which it's revolving or anything. So the underlying principle is a far more complicated than anything. So the way these works is, so there are only, in the D block, there is iron, cobalt and nickel, which exhibits ferromagnetic principles, and it comes from the quantum mechanics state. So you have 1s, 2s, 3s. Again, this length should be much larger than this length, but let's ignore that for now. So on and so forth, different orbital structure. So when you have ion, it has 26 electrons in its non-ionized state. So there will be 2 here, filling up the 8, 6 and 6, giving the 12, putting a total of 20, and then these would be 6 electrons. So we have a spin up, spin down, spin up, spin down, spin up, spin down. So this is a structure, and what basically creates the magnetic property that we see is the spin associated with these unpaired electrons in the d orbital. Right? The same thing happens with cobalt, same thing happens with nickel. Cobalt has one more paired electron which do not contribute, and then nickel has one more paired electron. So the other 2 remaining d orbital electrons which do not have a paired spin in the opposite polarity is what effectively creates the magnetic field that we see for ferromagnetic material. There is a little bit of issues here as well that needs to be addressed, which we won't do in this class. For instance, if you look at manganese, it in fact has 5 unpaired electrons in the d orbital, but it is not ferromagnetic at all. Any measurement you can make if manganese creates extremely poor ferromagnetic property. Right? So it's a little bit more complicated. Certain structures, certain pairing creates it to be more stable, and when the crystal lattice for manganese forms, it forms in such a way that not only the electron in this, so when we have manganese lattice, the neighboring 2 electrons must also have the same spin state for it to become ferromagnetic. But that's not what happens in manganese. Manganese somewhat arbitrarily chooses random directions. But iron, if formed under proper condition, the crystal lattice would be such a way that the electrons in the final d orbital would all align up in the same direction. Right? If they are in the opposite direction, that means an external magnetic field would be amplified by one atom, the neighboring atom would cancel it out. That's what makes it non-ferromagnetic for manganese. But when an iron lattice forms, iron crystal forms, certain case, when you quench it really fast and stuff like that, you can create this crystal lattice where there are domains which are created where all of these crystals have their d orbital electrons with the spin state in the same direction. So what then happens is when you apply an external magnetic field, all of these can align in the same direction, significantly amplifying the magnetic field that you can measure from the system. Right? So in our case, we don't care about too much about the origin of this. Right? If you're taking the advanced power electronic course, you might get into some of the devices, right? Go into some more detail, which would explore some of these areas and stuff. But for our case, it's not too much of a concern. So we can as well think of a simple scenario where, yep, there is a central orbital, there is some electron revolving around it, and it creates a magnetic field. For whatever reason it happens for some materials, for some other materials it don't happen. So our knowledge of, atomic model from early 1900s is quite good enough to carry on with the discussion for today. So we have this solenoid, we have an ion block inside. So once we start applying magnetic field, right, these are tiny elements, these dipoles. Right? Whenever I draw just an arrow upwards, it's completing it back, so it's a dipole. So these dipoles tend to align along the direction. So these are these electrons going around. Again, completely wrong model. It comes from the spin state, which basically measures the angular momentum of the electron. So completely unrelated. This would be the correct model. This is the wrong model, but we'll stick with it for simplicity. So we apply external magnetic field. All of these dipoles align along with external magnetic field, and they themselves create additional magnetic field, which amplifies the total magnetic field that we observe in case of iron. So what then happens is we can do experiments where we pass more and more current into the structure and look at what the B field looks like. As we pass more and more current, the B field increases. almost linearly. Okay? And the reason being that when the external magnetic field is small enough, so whenever the external magnetic field is trying to align these dipoles, just random thermodynamic process would keep on knocking them off. Because in general, they would be in all random orientation. It's just that the external magnetic field is aligning them in one particular direction, right? But left to thermodynamics, you take off this current given to the thermodynamic laws of nature, they'll again go back to their completely random state, right? So for every time, every set of molecules, every set of atoms that are being oriented in this particular case, or in case while the domains that are being oriented correctly, some part of the domains are again put in random order. So we have a bunch of them in this direction. There will be some in the opposite direction, some pointing in some random directions. But due to the external magnetic field, a significant portion would be along the direction in which the external magnetic field is. So, and as you keep strengthening this magnetic field, more and more are going to align along the direction that you have. So that's why we see that when we pass more and more current, the magnetic field due to the current is going to increase. That in turn is going to align more and more of these domains, which in turn is going to increase the magnetic field that we can measure. But this keeps on going until you have ended up aligning all the domains that are there within the ion. Right? Once you have aligned all the domains, what would happen to this magnetic field as I increase the current? Will it increase?
It'll saturate, right?
Saturate. By saturate, would it remain constant or?
I think it kind of looks like a transistor, like it slightly increases, but much slower.
Okay. So when it saturates, do you know at what rate this would increase it? So once this ion is fully, all the domains are completely aligned, it is same as if the ion is not there inside, right? That's just an add code. So the rate at which this would now increase would just be proportional to mu naught again, because our V itself was mu naught Ni divided by L, right? When we had this ion inside, it was strengthened because of this material that's inside. In that case, it ended up having, so we are going to represent that by some slope, mu r times, mu naught times Ni by L, mu r times mu naught, right? So when the ion is not saturated, again, this is an idealized curve. It won't be straight lines like this. So let's start off with an idealized curve and then look at the actual curve. So when the ion starts off without any of those domains aligned and we start increasing the current, more and more domains start to align. And as more and more aligned, the magnetic field is amplified significantly. But once all of them are aligned, it is basically as if it's an add code and it goes back to the same slope as mu naught, right? Everybody clear so far? So there now comes a big problem with our equation that we have. Is how do we explain? So our equation is integral B dot dl is equal to mu naught I enclosed. So we said this we can break it down into I conductor, which is what we know because that's the current we can measure, that's the current we put in. But this I material is problematic. We don't know what the material current is. Or basically this because there is no material current in the first place, just because of these alignments of these domains that we have, and there is no nice way of measuring them on a regular basis when we have an inductor or something like that. So what we have done is just do a little bit of mathematical jugglery to replace this. So let's say we have just a pure magnet alone, north and south. Here too the law applies, so in case of magnet. So that integral B dot dl equal to Ni mu naught times I enclosed applies here as well. In this case, there is no conductor current. This is just a pure magnet. So there is only material current. Okay, whatever that material current is, whatever Ampère was trying to signify it as. Right? So we are going to create use a new term for this. Instead of B, we are going to call it M, which is the material magnetic field. So whenever we have any kind of ferromagnetic material and where this term mu naught times I material, we can replace it by this new term, which is the material magnetic field closed integral of the loop integral of the material magnetic field over the loop that we have. Right? It's a pure mathematical jugglery. All I did is replace this term B with this term M to differentiate the magnetic field that's because of the material versus the magnetic field that is a combination of the current carrying conductor and the material magnetic field. All right. So when I use the term B going forward, it would mean the total magnetic field due to the current carrying conductor as well as the magnetic field amplified by the material. So let's go back. And replace our expression. So we have integral B dot dl equal to mu naught times I enclosed. This we are going to break it down into mu naught times I conductor, right, plus mu naught times I material. And this term is what we said we are going to now replace it with integral m dot dl. So we can take that to the left hand side. It becomes b minus m. Again, just pure mathematical swapping terms around without any physical implication for it. And I'm going to pull this mu naught term as well down. So b minus m divided by mu naught times dl equal to I conductor. And we are going to define a new term, pure definition called H, which is magnetic. Let me write it on the top here. So H equal to b minus m divided by mu naught. So this is magnetic field intensity. I wish they had used completely different name, but that's what it is. Magnetic field intensity, and the units is ampere per meter. So the reason for doing all of this is now it would allow us to write this equation that we have, the first equation there, in a different form, which is independent of the material property. So now our equation is now integral H dot dl over a closed loop is equal to I conductor. Right? So our first equation that we had before, which was integral B dot dl, is equal to mu naught times I enclosed. Right? There's a difference in the subscript that I have there. This I enclosed is a big problem when we put ferromagnetic material into the solenoid. We don't know what the I enclosed is. We know what the current in the conductor is. We don't know what the current of the material is or what equivalent current it represents. So we want to simplify it to a form where we can only use quantities that we can measure. So irrespective of whether it's a current in a solenoid, solenoid with an iron core or solenoid with an air core or solenoid with a wood or solenoid with a paramagnetic material, diamagnetic material, doesn't matter what the material is inside, this is always going to be the same. If the current in both the cases are same, H in both the cases are going to be exactly the same, right? It's independent of the material that we have. So, but this H itself is useless, right? It's a purely invented figment of our imagination. B is a real quantity because energy is stored in the B as we have just shown, right? Half of B square by 2 mu naught, half B square by 2 mu naught. But H does not have any such property. It's purely an invented mathematical entity that has no physical implication of what goes on in the real world. Okay? So then what do? When we have items with real world elements in between them, and B field is what we are interested in, not the H field. So material manufacturers would provide this chart. So what they would do is they would pass different currents. They would put a material inside a solenoid and they would pass this different currents, right? So let's say again this length is L, number of turns is N. So if I apply that integral H dot dl is equal to Ni, that implies H equal to Ni divided by L, right? Same as what derivation we have done before, just the mu naught term is missing compared to B. Okay, so instead of I can plot the x-axis as H, magnetic field intensity. So what I'm going to do is I'm going to pass different amounts of current. Start off with 0 ampere, pass 1 ampere, 2 ampere, 3 ampere, 4 ampere, so on and so forth, and measure what the magnetic field is coming out of the solenoid, right? And then I'm going to plot this. Right, for different points, and then I can interpolate it and close it. So this is what the curve ends up looking like. So in the initial part, when the core hasn't saturated, this slope has mu r times mu naught that we just saw before. And once it saturates deep into saturation, this slope is just mu naught as we just add code, the ion is not present at all. The y-axis is B units of Tesla. Alright, so this is going to be the BH curve of a material that has never been exposed to a magnetic field before. Alright, everybody clear so far? So given a circuit, what we'll do is when we go to motors, we'll have some current, we'll figure out what the H in the motor is, right? And to figure out what the B in the motor is, we'll have to go back and look at this map and figure out where the H is, and then go and figure out what the equivalent B at that particular point in the curve for the given current is, right? We cannot directly figure out the B of a complicated structure just by solving the equations that we have. So far, the material properties did not matter at all. Now the material property has come into the picture. And the material property is far more complicated than the equation set that we have so far. Right? So what we do for the material property is have this BH curve, which will tell us with a simple value of H, what the actual B value is going to be. So this is the real quantity, this is a pure figment of imagination that we have. Right? Everybody clear so far difference between B and H here?
So how do they measure, like when they're characterizing that, how do they measure H and B?
I think H you don't measure. So H is basically just putting a current sensor, right?
Okay.
So it's straightforward. Ni divided by N. N is the number of turns, L is the length of the solenoid, everything is known. B on the other hand, you would typically put like a Hall effect sensor or something, right? Some kind of magnetic sensor, right? So again, Hall effect sensor are all new inventions. Back in the day would have been like some kind of force experienced by some kind of current carrying conductor, and you measure that force, you can figure out what the E proportional B is going to be, right? Back in Ampere's day, I guess. Anybody any questions? Everybody clear the difference between B and H? That's a very critical distinction. Okay. So okay. So something interesting happens when we have material like iron. Typically in a motor and inductor, you would use this thing called silicon steel, right? Which basically iron. Iron, if you put carbon into it, it becomes stainless steel, right? Which makes it very hard. And in case when you induce it with some kind of silicon atom into it, to remove as much carbon out of it as possible. If possible, 0% carbon, and start introducing silicon into the lattice, typically around 0.5 to 3 to 4%. It provides some property where it amplifies the magnetic field, the mu r factor that we have, right? Pure iron is not doesn't have too much mu r compared to those that infuse with silicon, and it also improves something called the performance for eddy current losses, which we will take a look at next on Friday. But for now, the material that's used is silicon steel is basically iron with the crystal lattice where some points silicon are injected into. So when this material is first created and it has never been exposed to magnetic field in its life, it would give this characteristic curve that we just saw. So as you keep putting more and more current, so create a solenoid, insert the core into the solenoid, and as you start putting more and more currents, it is going to keep on increasing, and then it's going to saturate out with this being mu r, mu naught. And this mu r is typically around 6,000 for materials that we use in motors. And after that, it just becomes like air gap. So that's why I said the magnetic field, due to when you have an iron core, is orders of magnitude 6,000 times higher for a solenoid with iron compared to solenoid without iron inside its core. So it's much, much higher. Now, what interestingly happens is as I start reducing the current and take the current back to zero, it does not go back to where it started. It traces a different pathway. So when H goes to zero, that means the external current that I push through the solenoid has gone to zero. And yet the material magnetic field does not go to zero. Right? Anybody know what this cross-sectional point is called? Retentivity. Basically, whatever magnetic field that's retained or residual magnetism. So once you make the current go all the way down to zero, it still retains some magnetic field. This is what happens to magnets, right? So when you take out all the magnetic field, some of the domains still do not get knocked back off. Right? They have been somewhat embedded to a good extent that they retain their orientation and they retain the magnetic field that was imparted to them, and they don't go down to zero once you make the H field go all the way down to zero. Over time, those all would be knocked off by thermodynamic principle and as well as stray magnetic field. They would all be reoriented again. But how long that reorientation takes changes with material. So if you have these magnets that you used in high school, you'd have seen in your labs like the horseshoe magnets, which are basically these magnets that look like this. Right? These are magnets which would lose their magnetic field if you don't put the plate on top of it. They would lose their magnetic field within a couple of years. Right? Maximum 5 years, they would retain the magnetic field. When you have these neodymium magnets that are there in your phones and your laptops and all high-powered motors, those can retain the magnetic field for thousands or 10,000 years. Right? The amount of time they retain varies with material, but whatever remains is called the retentivity. And to make this magnetic field go back to zero, what you need to actually do is pass current now in the opposite direction. So the material that you previously excited has created a magnetic field in this direction. Right? Now to remove the retained magnetic field BR, you would have to put current in your conductor in the opposite direction, negative current, so that the current carrying conductor creates a magnetic field in the opposite direction, which can now knock out the remaining aligned domains to a random state so that the magnetic field comes down to zero. Anybody know what this point of the intersection is? One is retentivity, other one is coercivity. And give a meter. So it's just it will have a negative value. So you basically need to put some negative amount of current to knock them all so that the B field of the material comes back to zero. Now when you take this current and make this current go sinusoidal, so when the current was zero, it went up here, and then when the current came back to zero, it came down here, then the current goes negative, current goes even negative, and then the current goes back to zero, and then the current goes positive, current goes even more positive. It creates the loop where it keeps going back and forth, right? So this is called the VH curve. So when we have this pH curve, so let's go back to our energy expression. Okay, that was integral EI dt for power times dt, and our E itself was integral n times d phi by dt, and our current, if you remember, right there, H equal to Ni by L, Y N L HL by N, right, from this expression right here. So substituting that, HL by N times dt. So I'm substituting for the current, substituting for the EMF. And phi itself is B times the cross-sectional area of the solenoid. Cross-sectional area is not changing. So let me take the term out. So dV by dt times H times L divided by N times dt. dt goes away and N goes away. We end up with A times L times constants pull out of the integration, H times dV. Right? So as I pass current and I go through these cycles, so the currents vary cyclically. So I start off with zero current, go to some positive value, go back to zero current, go to some negative current value, go back to negative peak, and then come back to some amount of, come back to zero current, then push more positive current and go on and repeating the cycle. So whenever we pass sinusoidal currents to the motor, this is what the B field ends up looking like inside the motor. It keeps going through the cycles over and over and over again, right? And what I'm basically going to try and figure out is what the energy is going to be for the process of going through the cycle over and over and over again, right? So if I do this integral on the right hand side, which is integral, so when I do integral H dot dV, what does this represent in this curve over one full cycle? If I give you any curve and ask you to do an integration over a cycle, what does that integration represent? The area. Right? So if I give you like a circle and ask you to go around the circle and integrate the circle the length over the full radians from 0 to 2 pi, whatever you end up would be the area of the circle. Same thing here. So this integral h dot dv or integral b dot dh, however you want to do the integration along the y-axis or x-axis, is going to be the area under this curve. Right? So that area times A times L, and A times L itself was the volume of the solenoid, which we saw before. Right? So the energy is equal to the volume of the solenoid times area of the pH curve. Where is this energy going?
Thermal losses,
Thermal losses. What's the name for that energy?
like the losses?
Yeah.
Core losses?
Core losses. The core losses could be multiple different things. What subcategory within core loss is this? There's a MATLAB nonlinear toolbox that has this symbol. Yep.
Isn't it called just like BH loop losses?
Yep. But another name for it?
Hysteresis?
Hysteresis. Perfect. So the MATLAB nonlinear toolbox, if you look at the hysteresis toolbox symbol, you will have this. That's basically the diagram that we have there. Right? So this loss is called the hysteresis loss. So this energy is not stored in the magnetic field, right? So this energy is lost in the material. So every time the domains are aligned and unaligned, aligned and unaligned, they have create friction, which is then lost as thermal energy. So the core would start to heat up. All right, there's one component of core loss, the other being the eddy current loss. I'll take just 1 more minute, after that I'll be done. Okay, the video is recorded, those of you have to leave for another class or something, that's absolutely fine. So this is the hysteretic loss that comes about, and this is not the energy that's stored in the magnetic field, which is volume times turf b square by 2 mu naught, completely different. All right, so this energy is lost every time we go through one full cycle. The energy is gone and it cannot be recovered. Okay, so given this, how we choose our material matters. So let me draw 2 different BH curves. One that looks like that, and one that looks like. Again, it's symmetric. This my drawing is pretty bad. Right? So which of these two would you choose? Let me call this A, let me call this B. Which one would you prefer was the material used for magnets, and which one would you prefer is the material used for making a core of a motor or core of a solenoid, if I say?
Use A for magnets because it has higher retentivity.
Perfect. So this one has very high retentivity. So even after the current is gone, the magnetic field is retained. Right. So this is a very interesting, nice property to have in a magnet. Right. This is the only reason you want to use this is for a magnet. Right. There's one more reason. Yep.
Is it resistive to like currents? Like if our
Okay.
currents pass through it?
This matters too, because the coercivity is pushed far, far apart. So if you remember in the permanent magnet, one of the problems I said, if the rotor comes to a sudden stop, there's a huge current flows in the motor, which can then create magnetic field in the opposite direction, which can demagnetize a magnet. Right? So you want to push this as far away as possible so that even the external current stray magnetic field does not demagnetize the magnet that you have. So you want very large coercivity and large retentivity for a magnet. Okay, and Isaiah, why you would want this for the core?
These has smaller area, so smaller hysteresis losses, so it's better for like power electronics and motor design.
Perfect. So when you have for inductors or motors and you pass sinusoidal currents through them, right? Intentionally in case of AC motors or when you have power electronics where the ripple current has sinusoidal component, which was you saw in Fourier series, that varying sinusoidal component is going to be lost as energy in the core. Right? And if this area is extremely large, then it's going to dissipate a lot of heat in hysteretic loss. So you want to constrict the area as much as possible so that the loss is very limited to it. Right? So for core, you would use this with low area, very low pH area to limit losses. Right, so that's about it. So with that, we are done. We can meet again on Friday.